So what we're going to look at here is our carbonyl chemistry in this particular unit. If we want to consider kind of a review, we did evaluate the carbon-hydrogen bond in officially the last unit, but we kicked it into the second unit, and that hydrogen had some acidity due to it, and that was because we could do resonance with the carbonyl structure. And it's that kind of resonance that's going to draw out the chemistry that we're going to take advantage of in this unit. So let's back away from that acidic position and look at the carbonyl itself. Well, one of the things that kind of can help us interpret reactivity is if we go through and look at resonance structures. And if we look at our resonance structure, we should notice that we'll get a negative oxygen and that we will pull out a positive carbon. Okay? That kind of resonance is something that's useful for us because that can now give us some points of reference to determine reactivity. That negative charge is very likely to be basic or could be used as a base, and it could potentially act as a nucleophile. If we now try and push to differentiate between our base and our nucleophile, the base is going to be a little bit easier to access because that base is now reacting with H+. The nucleophile needs to react with an electrophile or E+. On the surface, that doesn't seem like that big of a deal, except that E+ is found within a molecule, which means that's going to be a little bit harder to access than the hydrogen. If we scaffold back out to our oxygen, the oxygen does have this kind of bulk hanging out behind it, which is going to make it a little bit sterically hindered and decrease the odds of it acting as a nucleophile. So our primary categorization for that oxygen is going to be seeing it act as a base. If we go through and look at the carbon, being positive makes it electrophilic, okay, which is great. We now have that potential electrophilic site. We don't have the same conflict as we had with the base nucleophile because it can't act as an acid because it's not a hydrogen. So if we now pull this all the way back through, we could go through and attempt to run some reactions with this. So let's clear everything away and say, hey, let's have this structure act as a base, which means we throw up an H+, we would get our reaction, and we would form a charged intermediate with that positive oxygen. This could be resonance stabilized, which is nice. But at the same time, what is that going to end up doing for us? That's going to still give us this very reactive electrophilic carbon. So while this acid-base chemistry is present and it is something we should consider, it's probably not going to be the driver of all of our chemistry for our carbonyls. Okay, so let's flip this and look at the electrophilic characteristics. And in the electrophilic characteristics, we've got that nucleophile coming in and attacking. This is going to force that pi bond to break, and we would now have the nucleophile connected and our oxygen with a negative charge, which could then very quickly undergo an acid-base reaction in a second step to put on that hydrogen, and we would now have a neutral species where our structure is potentially changed. This reaction is going to be a little bit more important to us because it's one we haven't studied yet. If we look at the overall process, beginning to end, we are starting with two pieces and they become one, which means we are doing an addition reaction. The next question would be, well, what are we adding? Okay, what did we react with? We have seen additions before where we reacted with electrophiles. In this case, it's a nucleophile. So we're running a nucleophilic addition. This is a new mechanism for us, and it's one that we can now take advantage of to show the expansion of different carbon structures. So this is the basic characteristics behind it. So now what we need to do is say, well, what could it react with? This is where we now run our substitution of all the different possible nucleophiles. Cardy separates it really into two sections. We get what I'm calling stupid strong nucleophiles, which isn't listed there. And because I can't spell, you'll usually see me drop it in with the double O. Okay, so stupid strong nucleophiles. Our stupid strong nucleophiles would be things that can't stabilize a negative charge very well. So we'd be looking at things that are very, very small and low in electronegativity. There's really only two elements in the organic chemist repertoire, at least the beginning organic chemist, and that's looking at hydrogen and carbon. Depending on the carbon source, you get a slightly different name associated with it. So we end up seeing some named reactions appear. Don't stress per se behind the naming. I want you to recognize the chemistry associated with those. And that is a little bit trickier because now you actually have to understand something as opposed to just blindly memorizing things. Naming, it turns out, is kind of an interesting debatable area or thing that has been in the news lately as far as named reactions go, because do we really need to associate someone's name with it? Okay? I would argue no, we need the chemistry, focus on the chemistry and the structures. The naming process is really just a simplification of the chemistry, okay? So that when you talk with someone, you can convey a bunch of information. However, we're moving through technology where we can actually bring in structures pretty quickly and efficiently. Let's switch to actually looking at the chemistry, not at the names of the people that did it. Just my 2 cents. Right? After we look at our strong nucleophiles, we transition. That Gilman reagent is actually kind of a transitioning reagent. And we'd move into our quote unquote weak nucleophiles. These are by no means weak, they're just weaker than the stupid strong nucleophiles. The strong nucleophiles of chapter 18 would be our oxygen and our nitrogen. We'll see another carbon one pop up in there with our cyanide as well. Okay, and that's kind of the big summary of those 2 chapters, is just how each of these reagents reacts with our carbonyl, and it's just kind of a mix match back and forth. Okay, well, of course we got the enolates. I left those off. Those are extra fun, which we'll see later too. After that, we get a little blank there, and then some relevant examples behind our ketones and aldehydes. Those functional groups are incredibly common in biochemistry, and they contribute to a wide array of chemical reactivities. So they will appear throughout your studies. Okay? They're arguably probably one of the more important functional groups for students to study in any kind of pre-health environment. So they show up a lot with our steroids. They also show up a lot in our different flavorings or scents. Okay? The names you're seeing associated here, don't stress about those because those are common names, and we really don't care about common names, or at least you're not responsible for them. What you're responsible for would be our IUPAC names and how you go through and name something according to actual rule sets. Admittedly, these rule sets aren't much fancier than the common names because the rule set was just, well, invented. It wasn't actually based off of any hard underlying facts. Okay? So with that, you should be able to go through and name these. To get you started, I'm going to go ahead and I'll actually name 2 of these, assuming my pen kicks in, and we'll take a look at this one up here and this one. First process that we should go through and do is identify our longest carbon chain. The red one's a little bit easier. We've got 1, 2, 3, 4, 5, 6, 7. So we're looking at a hept. If we look at that backbone, those are all carbon sp3-ish kind of backbones. So our hybridization would be alkanes. And we'd say heptane with that E. If we go back to the nomenclature system that I've got here, we look and we see that we have a ketone because we have that carbonyl in the middle of the carbon chain. The E part of our heptane needs to be changed to one. And we get heptanone. Okay? And that would be kind of our core name behind this. We do have to address where that ketone appeared in the chain. That would be at the 3 position. If we'd numbered right to left, we would have had a higher number. Higher numbers are bad because organic chemists can't count. Okay? So we would then move to the next one down, okay, kind of our blue structure. And we could see how this one changes it. Okay, we'll try and run the same color coding. We need to find our longest carbon chain. For those of you that look, you're probably saying, well, there's the longest carbon chain right through here with 8 carbons. And you would actually be wrong. Our longest carbon chain is actually going to run here. And you might say, well, Mike, 6 is smaller than 8. You are correct, but our longest carbon chain must contain the highest priority functional group. We have to include the carbonyl carbon as part of that chain. Okay, so we're actually looking at a hex, not an oct. Again, the backbone is all sp3, so we're looking at a hexane. That E changes out because we now have an aldehyde, because it's a carbonyl at the end of a chain, implied hydrogen. The E becomes al, and we get hexane now. Okay, officially, we should throw in a 1 in front of that, so we're extra explicit in reference to where that aldehyde is located. IUPAC has been pushing to little avail, based off of what I've seen or heard, that you should be putting that 1 as close as possible to the functional group you're referencing, so it should be hexane 1-al. We haven't finished because this piece has not been labeled yet. There's 1, 2, 3 carbons in there, so that would be a propyl. That propyl is connected at carbon number 2. Thankfully, we numbered it, and our final name would be 2-propyl hexane 1-al, and we've got our name. Okay, so with that, I'm going to try and leave that there, and then what I'm going to attempt to do is, with the magic of pause the lecture recording, see if that actually worked. If that worked correctly, what you now see are all of the answers scattered up there. You should have been able to get to those answers. It can be tricky to deal with nomenclature, but again, it's just a rule. You have to know the rule. Okay? If you don't know the rule, it just takes time to figure out what the rule is. With that, I'm going to go ahead and clear the screen and hopefully see that it was actually recording for at least some of that. Cool. And we'll go ahead and advance on to the next kind of background stuff behind this. Chapter 17, here's our spider diagram that covers all of our big reactions. We're going to start off chapter 17 by looking at our hydrides. We'll then move into our Grignards with maybe a light discussion on the acetylides. That one I kind of float off because it's sort of a first semester reaction. Then we will look at our, well, officially our alkyl lithiums, kind of group in with our Grignard. Then we'll see our Wittig reaction. And then we'll end with the kind of unfortunate one with our Gilman reactions, because the Gilman branch out between those. So that's kind of our weird diagram of everything that is chapter 17. Be familiar with these, recognize some of the chemistries associated with them. For those of you looking really carefully, let's go ahead and clear all of that away. And let's just focus up here. You should note that that carbon does become a stereocenter. And we could theoretically have discussions about that stereocenter. Interestingly enough, most discussions or textbooks seem to ignore really the stereochemistry there, and we don't have to worry about it at all. That doesn't mean it's not present. There is a stereocenter there, and it can become really important. But there is very little reagents that we discuss that preference one stereocenter over the other. If there's no preferencing, then typically organic chemists just don't talk about it, and we just don't show it. Okay, but realize there is a favoring there. What does that favoring do to? That was a pause to ask a question and a quiz question, but I don't think I'm going to do that. It's actually because you're reacting pi bonds. Okay? Those pi bonds are coming from the p orbital. Oof, that was an ugly p orbital. But those p orbitals the hydrogen or our carbon or whatever our nucleophile is could come in from the top or from the bottom, which means we get two potential products coming out of this, like with most of our addition reactions. And then the last thing we'll address will be chapter 18, not quite as prettily organized, but it does show some overlap with some of the other functional groups or with our carbons. And we'll be looking at our oxygen nucleophiles and our nitrogen nucleophiles and how they change the dynamic. A large percentage of that chapter or our discussion of that chapter is going to be looking at this functional group, the acetal. If you're moving into biochemistry, that's a pretty critical functional group. Okay, that's all of our carbohydrates. Okay. With that, I am about 90% certain that that is the end of our overarching review of this entire unit, but we'll go ahead and hit next just to see what pops up. And yep, that would actually be starting our next lecture. So we'll backtrack a little bit and say thank you for listening and good luck. Let's actually stop the recording. If I can find my mouse.